Welcome to the deep dive. What if I told you that, like, 90% of the time, the most expensive, most critical appliance in your entire home was chosen completely by guessing?
I mean, it sounds totally absurd, really,
Hmm.
but it's actually the reality of the residential heating and cooling industry. It's the definition of a multi-billion-dollar guessing game.
Wow.
And the crazy part is, the homeowner almost never realizes they're the one losing that game.
Okay, let's unpack this,
Okay.
because we are looking at some really incredible source material today.
Yeah, we are.
We've got an industry insider transcript from the Cool Talk show,
Yeah.
the actual technical sizing standards published by ACCA, that's the Air Conditioning Contractors of America,
Yeah.
and some really fascinating performance data regarding heat pump balance points from HVAC today.
Right, which is super technical stuff, but so important.
Exactly. And the mission of this deep dive is to completely change how you view the climate in your own living room. We're going to uncover why your air conditioning unit is almost certainly the wrong size, how this hidden error is just like quietly costing you thousands of dollars, and why it's secretly the reason your house never quite feels perfectly comfortable.
Because, I mean, if you think about it, usually when we talk about a major purchase for your home, we demand absolute precision.
Oh, absolutely. Like if you're putting in a new kitchen island, the contractor measures the space down to the millimeter.
Exactly.
They check the clearance for the fridge door,
Yeah.
the height of the stools, because if it's off by even an inch, the whole flow of the room is ruined, and you notice it immediately.
Right, but they
Then,
give percent.
yeah, you step outside to look at a $10,000 or $15,000 air conditioning unit, and suddenly that tape measure just gets thrown out the window.
Yeah.
According to the industry's own data, 90% of residential systems are sized using a completely flawed rule of thumb, which leads to massively oversized machines.
It's staggering when you put a hard number on it like that, 90%. And to really understand why this happens, you have to look at the psychology and the incentives of the contractor who's doing the installation.
Right. Like, what's in it for them?
Exactly. When a contractor comes to your house to give you a quote, they typically just look at your total square footage and divide it by some random number.
Like, what kind of number?
Oh, say 400 square feet per ton of cooling capacity. Or honestly, even worse, they just look at the rusted metal box sitting in your yard and say, well, you had a 3-ton unit before. Let's just put a 3-ton unit back in.
So they're literally just trusting the guy from 15 years ago who also probably guessed.
Yes, exactly.
That's just this generational cycle of bad math.
It really is.
But, I mean, why default to that? Why not just figure out the real number?
Well, it all comes down to risk management and callbacks.
Callback.
Yeah. Let's say a contractor puts in a system that is slightly undersized. If we get a brutal heat wave in August, the homeowner is going to call them up complaining that the house is hot.
Oh, and nobody wants that phone call.
Right. The contractor has to drive all the way back out there, deal with an angry customer, and, might even have to eat the cost of replacing that unit.
Ouch. Yeah, that's a huge loss.
But if they massively oversize the unit, the house gets cold. And nobody ever complains about a cold house in August.
Oh, wow. I never thought about that.
Yeah, the contractor avoids a callback, they get paid, and they go home. It's safe.
So the entire industry has this, like, built-in systemic bias toward oversizing just to cover their own bases.
100%.
But they are actively ignoring the actual solution, because there is a right way to do this. Right?
Oh, absolutely. There's an absolute gold standard. It's an industry standard called Manual J, which is published by ACCA.
Okay, Manual J.
Right. And it's not a guess. It is a rigorous mathematical load calculation.
Well, let's get into the weeds on Manual J, because I think most of us assume measuring square footage is like enough of a calculation.
Yeah.
What else is there to even measure?
Oh, square footage is barely the tip of the iceberg. A proper Manual J calculation requires the contractor to measure the specific window area in every single room.
Wow, every room.
Every room. And they have to account for window orientation. Like, are those windows facing the baking afternoon sun in the west, or are they completely shaded in the north?
That makes a huge difference, yeah.
It does. They also measure ceiling heights. They evaluate the exact type and R value of the insulation in your walls and your attic.
Wait, R value. I see that on insulation at the hardware store all the time, but what does that actually factor into the math?
Yeah, so R value is literally just a material's resistance to heat transfer.
Okay.
A thick, foam insulated wall resists the transfer of outside heat way better than a thin fiberglass roll. The software needs to know exactly how much heat is bleeding through your specific walls.
That is incredibly detailed.
it gets better. They also test for air infiltration. They look at your specific local climate zone, and this is crazy. They even calculate the body heat generated by the number of people living there.
You're kidding.
Nope. And the thermal output of the appliances inside the kitchen, everything goes into this calculation.
So you're basically building a complete thermodynamic model of the house.
Exactly. You plug all of those distinct variables into this specialized software, and it calculates a highly precise number in BTUs per hour for both your cooling and your heating loads.
Okay, and a BTU is a British thermal unit, right? Which is basically just a measurement of heat energy.
Correct, yeah. 1 BTU is the amount of energy required to heat or cool 1 pound of water by 1 degree Fahrenheit.
Okay, got it.
So the software tells the contractor exactly how many BTUs the house gains on a hot day, and therefore exactly how much cooling power the air conditioner needs to push back.
But according to the Cool Talk transcript we reviewed, fewer than 10% of contractors actually do this math.
Yeah, it's pretty bleak.
If the tool exists and it guarantees like thermodynamic perfection, I don't understand why a professional would ever skip it.
Honestly. Time is money. A thorough manual J calculation on a standard 1,500 to 2,500 square foot home takes about an hour and a half of meticulous on-site measuring.
Oh, wow. That's a lot of time.
And that's just the measuring. Then it takes another hour back at the office, sitting in front of the software, entering all that data.
Right.
So that's half a day of unbilled work just to give a homeowner a more accurate quote. In a highly competitive market where contractors are, trying to hit 3 or 4 houses a day to give free estimates, they simply skip it.
Okay, well, I want to play devil's advocate for a second. Let's put ourselves in the shoes of the listener sitting at the kitchen table.
Sure.
I get quotes from 2 guys. One actually does the math and recommends a 3-ton system. The rule of thumb guy skips the math but recommends a 4-ton system for roughly the same price. Intuitively, I'm thinking, if this contractor is willing to give me a bigger machine and my house is going to cool down incredibly fast, why should I care if he guessed? Like, isn't a bigger engine in a pickup truck always better if you want to pull more weight?
Yeah, that is the exact psychological trap that catches 90% of homeowners. You're applying automotive logic to thermodynamics, and it completely backfires.
Really?
Oh, absolutely. With an air conditioner, bigger is actually the enemy of comfort.
Well, let's test that, because if a bigger AC unit blasts my living room with cold air, it's doing its job, right? The thermostat drops. What is the machine failing to do?
Okay, so to understand the failure, you have to realize that an air conditioner actually has 2 completely distinct jobs.
2 jobs.
Right. The first job is what we call sensible cooling.
Sensible cooling. Okay, that just means dropping the temperature on the thermostat, right? Like,
Oh,
it's the cooling I can literally sense on my skin.
exactly. But the second job is latent cooling. Latent cooling is the process of removing humidity, like wringing the water out of the air inside your home.
Oh, okay. And if the system is oversized, if it has that bigger engine, it must be terrible at latent cooling. Why is that?
What's fascinating here is it all comes down to the timing required for latent cooling. Dropping the temperature. The sensible cooling can happen very fast if you have a massive machine.
Right.
But latent cooling, the dehumidification, that only begins to happen when warm, moist air moves across a freezing cold coil for a sustained, uninterrupted period.
Yeah.
The indoor coil has to get cold, and it has to stay cold. We're talking 20, 30, maybe even 40 minutes per cycle for the system to effectively pull water out of the air.
Okay, so if we look at that oversized system, it's essentially bullying your house. It blasts this overwhelming amount of cold air, satisfies the thermostat's temperature setting in like 8 minutes, and then it just completely shuts off.
Yeah.
It sits idle for 20 minutes until the house warms up, and then it kicks back on for another aggressive 8-minute sprint.
Exactly. The industry calls that short cycling. And because it only ran for 8 minutes, the coil never had the sustained runtime needed to actually wring the water out of the air.
Which creates a scenario that I think every listener has experienced at some point. You look at the thermostat on the wall, and it confidently says it's 74 degrees in the house.
Oh, yeah.
But the humidity level is sitting at 65%. And the environment feels absolutely gross. It's clammy, it's sticky, your skin feels damp, and you're sitting on your couch shivering, but also sweating at the same time.
It is a miserable feeling. And people try to fix it by turning the thermostat down even lower to 70 or 68 degrees.
Which just makes it worse.
Yeah. That just drives their energy bill through the roof and makes the house feel like a damn icebox.
Right.
Compare that to a properly sized system that runs a nice, long cycle. It holds the house at 74 degrees, but drops the humidity down to a perfect 50%. The air feels light, it's crisp, and it's incredibly comfortable.
You know, it sounds exactly like driving a car across town. A properly sized air conditioner is like getting on the highway,
Right.
setting the cruise control to 65 miles per hour, and just smoothly, efficiently gliding to your destination.
That's a great way to put it.
And an oversized air conditioner is like a driver who floors the gas pedal, sprints to 80 miles per hour, slams on the brakes at the next red light, waits, and then floors it again.
Yeah, and that slamming on the gas and brakes doesn't just ruin how the house feels. It absolutely destroys the mechanical equipment.
Let's dig into that mechanical toll, actually.
Yeah.
Because we established the comfort issue, but what is physically happening inside that metal box out in the yard during all these short cycles?
It is pure mechanical stress, specifically on the compressor, which is the heart and the absolute most expensive part of the system.
Okay.
Every single time a compressor starts up from zero, it requires a massive surge of electricity. It draws 3 to 5 times its normal running amperage just for those first few seconds to get the motor spinning.
Wait, 3 to 5 times the power?
Yeah.
Just to clarify amperage for everyone, if we think of electricity like water flowing through a pipe, voltage is the water pressure, but amperage is the actual volume of water flowing through.
Yeah.
So the compressor needs this massive, violent tidal wave of electricity just to wake up.
Exactly, and that electrical spike intensely heats up the internal windings of the motor. It stresses the start components. It wears down the electrical contactors.
So if we look at the math of machine death here, and we compare two identical compressors, one is in a properly sized system, and the other is in the oversized, short cycling system.
Right, so the properly sized compressor might turn on and run 10 long, slow, gentle cycles throughout the day. Because it isn't constantly enduring that violent startup spike, it runs cool and steady.
Okay.
That compressor will easily last 20 years. Now take the oversized compressor. It might run the exact same number of total hours, but it's doing it in 40 short, aggressive cycles a day.
Wow.
40 massive electrical spikes. 40 times heating up the windings. That compressor is going to burn itself out and die in 8 years.
That is insane. By demanding the bigger truck, you're literally guaranteeing you'll have to buy a whole new truck in half the time.
Yeah, you really are.
And there's a brilliant real-world anecdote in the Cool Talk transcript that perfectly illustrates this.
Oh, you're talking about the house in Hennessy, Oklahoma.
Yes. Here's where it gets really interesting.
Yeah.
So a contractor is called out to a house in Hennessy. The homeowner is incredibly frustrated. They had a massive 4-ton system installed just 2 years prior by a different company.
Right.
But their electric bills are astronomical, the house feels like a humid swamp, and they're convinced this brand new unit is just a lemon.
And the new contractor doesn't guess. He actually spends the time to run a full ACCA manual J-load calculation.
And the math reveals the truth. The actual cooling load on that house was only 2.5 tons.
Wow.
Yeah, the previous guy put in a 4-ton unit simply because the original broken unit was a 4-ton, and that original unit was oversized to begin with.
Right, so the homeowner was a victim of that generational guessing cycle we talked about.
Exactly. So they pull out the massive 4-ton unit and replace it with a much smaller, properly sized 2.5-ton 2-stage system.
And the results were instant.
Yep.
The homeowner's electric bill dropped by over $100 a month. The sticky humidity completely vanished because the smaller unit was finally running long enough to wring the water out of the air.
Amazing.
The homeowner had been paying for 60% more capacity than the house could ever physically use, 60% more upfront cost, massive electric bills, terrible comfort, and a machine that was eating itself alive.
It's a profound failure on literally every dimension. But to be entirely fair to the complexities of HVAC design, we really have to address a specific nuance here.
Okay.
We've totally debunked the bigger is better myth for standard air conditioning. But is there ever a scenario where you actually want an oversized system?
I was just thinking about that. Because we're looking at data from HVAC today regarding heat pumps, and heat pumps sort of change the math, don't they?
They do, yeah.
Yeah.
Specifically when we talk about the balance point,
Right.
A heat pump does both cooling in the summer and heating in the winter. The balance point is the exact outside temperature where the heat pump's heating output perfectly matches the heat loss of the house.
Okay, so what happens when it drops below that point?
If the temperature drops below that balance point, the heat pump can't keep up. And you have to use expensive supplemental heat, like electric heat strips.
So climate geography really dictates the rules here.
Absolutely. If you live in a very cold climate, say Minnesota, your heating load in January is massively higher than your cooling load in July.
Makes sense.
In that specific scenario, a contractor might intentionally oversize your heat pump's cooling capacity slightly.
Okay, so they're compensating for the winter.
Exactly. The system might be a bit oversized for the summer, but it guarantees you have a larger compressor pushing enough heat to handle those freezing Minnesota mornings without relying on emergency heat strips.
But if you live somewhere where the cooling and heating loads are relatively similar, like the Oklahoma example in the sources, that exception completely vanishes.
Totally. In a balanced climate, oversizing ruins the summer and doesn't provide enough winter benefit to justify the mechanical damage.
Which leads us right into the biggest psychological hurdle homeowners face, the worst day fallacy.
Oh, yes. Let's talk about the hottest day of the year.
Yeah.
Because this is the root of the fear that drives all this rule of thumb guessing.
Right. Rule of thumb sizing tries to build a system specifically to conquer the absolute worst day of the year.
Okay.
Let's say it's a 105-degree August afternoon. The contractor wants machines so big it can easily blast the house down to 70 degrees on that one single day. But that's the wrong mathematical question to ask.
Because, I mean, how many 105-degree days do we actually get?
Exactly. A perfectly sized manual J system isn't designed for one afternoon. It's designed for thousands of hours of standard performance across the entire year.
Right.
On that rare 105-degree day, a properly sized system will run almost continuously. It might cycle off for just 10 minutes an hour. It'll just barely keep up.
See, I know that hearing a contractor say, your new $10,000 machine will just barely keep up is absolutely terrifying to a homeowner. You want power in reserve.
It sounds scary for sure, but it is thermodynamic perfection. Running continuously on the worst day of the year is exactly what the machine was engineered to do.
Wait, really? By design?
By design, by
Okay.
running continuously, it's achieving absolute peak latent cooling. Your house will sit at the set temperature, but more importantly, the humidity will be bone dry.
Oh, right.
It will feel incredibly comfortable, and the moment the sun goes down, the system easily catches up.
Well, we've diagnosed this massive industry-wide problem. We know why contractors guess, we know the physics of why it ruins your comfort, and we know it destroys the equipment. Now we really need a practical playbook for you, the listener.
Yeah, how do you protect yourself?
It starts with knowing the actual standard of care, which the industry calls the QMAS package.
Let's break down QMAS.
It stands for Quality Installation, and it relies on 3 specific ACCA manuals. Manual J calculates the thermal load of the house. Manual S takes that load calculation and selects the exact piece of mechanical equipment that matches it. And Manual D is the proper design of the ductwork to deliver that air.
I want to expand on Manual S and D, actually, because those seem just as important as the load calculation.
Oh, they are.
Manual J just tells you the house needs, say, 30,000 BTUs of cooling. Manual S is looking at manufacturer data to find the specific machine that delivers exactly 30,000 BTUs at your local temperature.
Because machines perform differently in different climates, right?
Exactly. A 3-ton unit in dry Arizona performs very differently than a 3-ton unit in humid Florida.
And Manual D calculates the friction and static pressure inside the ductwork. You can have the perfect machine, but if the ducts are too small, the air never reaches the furthest bedroom and just gets trapped in the hallway.
Right. So what does this all mean for you when the contractor's truck pulls into your driveway?
Well, we've boiled this down to 3 highly specific questions you absolutely must ask before signing any contract.
Question number 1. Did you do a manual J-load calculation, and can I see the full room-by-room printout?
The key here is the full printout. If they hand you a 1-page summary with a single number on it, or if they look at you and say, oh, I just used what was already there, you kick them out of your house. It means they guessed.
Question number 2. What design temperature did you use?
This one is critical because contractors who are forced to do a manual J will sometimes try to cheat the math to get the bigger system anyway.
Really? How?
ACCA publishes historical weather data. If the manual says your local design temperature the average high for your area is 97 degrees, but the contractor manually entered 110 degrees into the software just to be safe.
Oh, wow.
Yeah, they're deliberately manipulating the variables to oversize the equipment. You have to ensure they used accurate local data.
Good to know. And finally, question number 3. Can I have a 2-stage or variable speed system?
Why is variable speed the ultimate insurance policy?
Well, even if the manual J sizing is slightly off, a two-stage or variable speed system doesn't just have a blunt on and off switch like a standard unit.
Okay.
It can throttle its capacity down. It can run at 50% power, creating those incredibly long, gentle, dehumidifying cycles, adapting to exactly what the house needs at any given moment.
Armed with these questions, you're still going to face a major psychological hurdle at the kitchen table when you look at the quotes.
Definitely, because when you finally find a good contractor who genuinely does the math, they're very likely going to slide a piece of paper across the table that quotes a smaller system than the one currently sitting in your yard.
Right.
And every instinct in your brain is going to scream that you're getting ripped off.
Yeah.
You're paying thousands of dollars, and they're giving you less machine.
Less is more is a really hard concept to swallow when you're writing a massive check.
But you have to push past that feeling. The math is absolute. That smaller, mathematically sized equipment is going to outperform the bloated giant in your yard on every single metric that actually matters to your life.
Let's recap this journey because it is so counterintuitive. Trusting the actual math over a lazy rule of thumb guarantees you lower monthly electric bills.
Yep.
It literally doubles the lifespan of your equipment by stopping the violent mechanical stress of short cycling.
Exactly.
And perhaps most importantly for your daily life, it's the absolute end of that clammy, sticky, damp, cold feeling in your living room.
You know, if we zoom out from your living room, there's a deeply provocative thought that emerges from all this source material. We've been focusing on the micro level, your house, your comfort, your wallet. But let's look at the macro level, the national power grid.
Oh, wow. I haven't even considered the grid impact of all this.
Think about the sheer scale of the problem. If 90% of the air conditioners in America are massively oversized.
That's tens of millions of machines.
Right. Picture an entire city at 3 o'clock in the afternoon on a scorching August day. Instead of millions of properly sized machines steadily cruising along, you have tens of millions of bloated machines constantly turning off and then aggressively slamming back on.
And every single time they slam back on, they're demanding that massive tidal wave of electricity.
Yes.
3 to 5 times their running amperage, all hitting the electrical grid simultaneously, 40 times a day per house.
Exactly. So how much of our national energy grid strain in the peak of summer is entirely self-inflicted?
That is wild to think about.
Imagine the sweeping reduction in global energy consumption if contractors simply took 1 hour to do the math. We're forcing millions of homes to run violently power-hungry machines, causing rolling blackouts and brownouts purely because an industry refuses to measure a window. The cumulative waste of energy is astronomical.
It completely reframes the entire issue. It's not just about a sticky living room. It's about a systemic failure of efficiency.
It really is.
And it all comes back to that initial idea we started with. We expect precision in a medical diagnosis. We demand precision when a carpenter cuts a cabinet. But we've let the most expensive appliance in our homes be dictated by a shrug and a guess.
Exactly.
It's time to stop letting them guess with your money and your comfort. The next time that contractor's truck pulls into your driveway, you look them in the eye and make them do the math.
And if they won't, find somebody who will.
That's a wrap for today. Keep asking the right questions, and we'll catch you on the next deep dive.